In this video, we will have a look at simple and multiple linear regression, and we will also consider nonlinear regression. To start off, have a look at this plot over here, which contains the returns data from two equity indexes x and y. So along the x-axis, here we have the daily returns of an index x, and along the y-axis, we have the daily returns of an index y. They're clearly very strongly related. When x tends to be big, y tends to be big as well, and when x is small, y tends to be small also. And the data looks like it is roughly in a straight line, and so we postulate an essentially linear relationship between x and y. In other words, y is equal to beta 0 plus beta 1 times x, plus some noise, and that noise is what makes this relationship deviate from a perfect straight line. Now, if we knew the values of beta 0 and beta 1, and we also knew the value of the returns x on a particular day, then we could use it to predict the value of y. An estimate of the value of y would simply be beta 0 plus beta 1 times the value of x. Now below here in this plot, we have drawn three lines, y is equal to beta 0 plus beta 1 times x, for three different pairs beta 0, beta 1. Now, as you can see quite clearly, the red line is quite a good fit. It's better than the green line, and both of those are a lot better than the magenta line. So the question is, how do we find the line that fits best? What do we mean by best? In other words, how do we obtain the optimal values of beta 0 and beta 1, and what do we mean by optimal? So let's set up the problem properly. We have two random variables x and y, which denote the returns of two stock indices, respectively. And we have many draws xi and yi from the joint distribution of those two random variables x and y. One draw for every day, say. Then we have a model of the form yi is equal to beta 0 plus beta 1 times xi plus some noise epsilon I. And we assume that the conditional expectation of epsilon I given xi is equal to 0. For example, the noise might be independent of x. Similarly, we will assume that the conditional variance is sigma squared. Now, the random variable x here is called the regressor, or the covariate, or predictor, or feature. The word feature is used in machine learning. And y is called the response variable. Here, beta 0 and beta 1 are given hats to denote that they are estimates of the true values of beta 0 and beta 1. If you had a slightly different data set drawn from the same distribution, you would obtain slightly different values of beta 0 and beta 1. And these are called the regression coefficients. Now, given beta 0 hat and beta 1 hat and the value xi, we would predict the value of yi to be simply beta 0 hat plus beta 1 hat times xi. And that's the fitted value of yi. On the other hand, that might not be exactly the same as the true value of yi because of the noise, and epsilon hat I is precisely the difference between the true value and the fitted value, and those are called the residuals. Given data points xi and yi now for y is equal to 1 to n, we estimate the regression coefficients, in other words the optimal beta 0 and beta 1 that we're looking for, as follows. The best choices of beta 0, beta 1 are those estimates that minimize the sum of the squares of the residuals. In other words, we regard this as a function of beta 0 and beta 1, and we minimize it. So the least squares estimate, beta 0 hat, beta 1 hat, minimizes the residual sum of the squares. Okay, so let's perform this optimization. We have a function here, f of beta 0, beta 1, which is just the sum of the residuals. And it's a quadratic in beta 0 and beta 1, and therefore should be easy to minimize just using ordinary calculus. We compute the partial derivatives, and we set them both equal to 0. So we have two equations in two unknowns here. I'm not going to go through these derivations verbally on the slide because it's very difficult to do. You can go through this calculation yourself and obtain that the partial derivative of f with respect to beta 0 is equal to 0 precisely when beta 0 is equal to the mean of y minus beta 1 times the mean of x. In that case, we have beta 0 in terms of beta 1, but we do not yet know who beta 0 and beta 1 are. We need one more equation. For the second equation, we set the partial derivative of f with respect to beta 1 equal to 0. When we differentiate it, we obtain an expression that looks like this. And we have already an expression for beta 0 on the previous slide. Beta 0 is just equal to y bar minus beta 1 times x bar. And so we compute, set it equal to 0, and obtain a value for beta 1. Now that we have the value for beta 1, we can put that back into the value for beta 0. However, it's convenient to manipulate this expression slightly by observing that whenever you have an expression of the form sum from I is equal to 1 up to n of zi minus z bar, where z bar is the mean of the zi's, times some xi, that is exactly equal to this sum of these products shown over here. And that's simply because the sum of zi minus z bar is equal to 0. If we apply this observation with z is equal to y in the numerator and z is equal to x in the denominator for the expression of beta 1 that we obtained before, then beta 1 looks like this expression over here. And that is equivalent to the sample covariance at the top and the sample variance of x at the bottom. Now, since the covariance of x and y is just the correlation times the product of their standard deviations, this simplifies to the correlation between x and y times the standard deviation of y divided through by the standard deviation of x. Once we know who beta 1 is, we can compute beta 0 using the equation that we obtained earlier. This gives us the optimal parameters beta 0 and beta 1 in a least square sense, because we minimized the sum of the squares of the differences between the predicted values or fitted values of y and the actual values or observed values of y. Let's consider an example. Here we have daily data xi, yi for I is equal to 1 to n of some financial variables x and y, which might be returns or yields or anything else that comes to mind. Suppose that the covariance matrix for x and y is given by the matrix with entries 4, 1.6, 1.6 and 1, and that means that the variance of x is 4, the variance of y is 1, and the covariance between x and y is 1.6. We're also told that the mean of the x values is 2 and the mean of the y values is 3. On day n plus 1, it is observed that the x value takes on the value 2.5, and we want to know what is the predicted value for the y on that day. So from the matrix, we see that the covariance between x and y is 1.6, and that the variance for x is 4. And hence, one of our expressions was that beta 1 hat is the covariance between x and y divided by the variance of x. That's 1.6 divided by 4, in other words 0.4. Then the equation for beta 0 says that beta 0 hat is the mean of y minus beta 1 times the mean of x, and that turns out to be 2.2. It follows now that yn plus 1 is predicted to be beta 0 hat plus beta 1 hat times xn plus 1. That's 2.2 plus 0.4 times 2.5. That's 3.2. You could also have computed the correlation from the covariance matrix. The correlation between x and y is just the covariance divided by the product of the standard deviations. So that's 1.6 divided by the product of the square roots of 4 and 1. And that's 0.8. And then we could compute beta 1 hat as the correlation times the standard deviation of y divided by the standard deviation of x, and we would obtain the same result. So far we've looked at simple linear regression, where y is assumed to be a linear function of a single variable x. In general, however, y might be a function of many variables, and moreover, the relationship might not be linear at all. So regression is a method for studying the relationship between a response variable y and a covariate x, and this x might be multidimensional. In particular, we would like to express the relationship between x and y in a functional form, r of x, where r of x is the conditional expectation of y, given that we know that capital X is equal to x. In general, R of x will be assumed to have a particular functional form, and so we typically won't get exactly the conditional expectation, but something that approximates it. We attempt to estimate the coefficients of the functional form for R of x from the data that's observed. For multiple linear regression, the functional form is assumed to be linear. In other words, we attempt to fit a variable y as a linear function of the regressor variables x1, x2 up to xp. So y is given as a linear function, beta 0 plus beta 1 times x1 plus beta 2 times x2 plus all the way down to beta p times xp plus some noise. And the unknowns here that need to be estimated are the values beta 0, beta 1 up to beta p. Here the regression function is therefore a linear function of x1 up to xp with coefficients beta 0 up to beta p. Observe that the regression function can be written also as a kind of matrix product of the x values and the beta values. We have such a matrix equation for each of our sets of observations. In other words, given n observations of the p many x values and the value of y for I is equal to 1 up to n, we can write yi as a row matrix of x values plus a column matrix of beta values plus some noise, epsilon I. Here the row values of xi's consist of 1, xi1, xi2 up to xip, and the vector beta consists of beta 0, beta 1 up to beta p. And as I said, epsilon I is just a noise term. When we put all of these equations together for I is equal to 1 up to capital N, we get a matrix equation of the form y is equal to x beta plus epsilon, where x is a matrix of the x values that we observe. In other words, the ith row of x consists of all the observations of the x values on the ith day. Y is a vector of the y values that we observe, and epsilon is a vector of all the noise terms. In other words, y is equal to x times beta plus epsilon with the dimensions of each of these objects shown here below. The predicted value of y is therefore x times beta. Now we'd obviously like the predicted value to lie as close to the actual value as possible. The least square estimate of the regression coefficient vector beta is that vector beta which makes x beta lie as close to y as possible. In other words, it's the vector which minimizes the distance from the vector y to the vector x beta. Now that distance is given by the length of the vector y minus x beta, which is just the square root of the sum of the squares of the differences. Here we have put xi0 equal to 1. It's the first entry of the vector of x values that we saw on the previous slides. Now solving this problem is equivalent to finding the vector beta which minimizes the square distance, which removes the square root sign here, and that's often easier to solve. Observe that when we're trying to write y as x times beta, what we're actually trying to do is we're trying to write y as a linear combination of the columns of the vector x. That's because if A is a matrix and x is a vector, then A times x is a linear combination of the columns of A with coefficients, the entries in the vector x. We are therefore interested in computing the vector of regression coefficients beta. On the next two slides, it's shown how this can be done using matrix calculus, which I won't cover here and is for general interest only. We're only interested in the results. These two slides show how you can differentiate with respect to a vector. For example, we're differentiating a function with respect to a vector that gives us the gradient that we covered before when we did gradient descent. And it is shown, for example, how to differentiate expressions of this particular form. We can use matrix calculus to minimize the square distance from y to x beta, which can be written as a product like this and differentiated with respect to beta using the techniques on the previous two slides. And it turns out that the optimal beta is given as follows. Het beta is equal to x transpose times x inverse multiplied by x transpose times y. Here remember that x is just a matrix of all the x values. and y is the vector of all the y values. This equation is called the normal equation for beta. Now, because of numerical errors in computing this inverse, it may be desirable to use an optimization routine to compute beta hat instead. In other words, you could minimize the function f beta directly rather than using the normal equation. This may be important particularly if the matrix X is very large. As an example, we consider the fitting of a polynomial to data using regression. Suppose that we're given data points x1, y1 up to xn, yn, where x and y are both one-dimensional, and we believe that y has a functional form y is equal to g of x plus noise, where g is a polynomial of degree p. We can then apply multiple linear regression by using the regressor not just x itself, but also the powers of x. In other words, the regressors are x, x squared, x cubed, all the way up to x to the power p. Then the matrix of x values that we obtain is the matrix whose ith row consists of 1, followed by the powers of xi. And we can solve that as before using the normal equation. Now, if p is equal to n minus 1, then we can fit the data exactly, and we have polynomial interpolation, in which case, in fact, this matrix X is just the Vandermonde matrix that we saw before when we did interpolation. As I mentioned on the previous slide, in practice you may find that the normal equation method fails for large p because of numerical errors, and you may have to resort to using an optimization routine such as gradient descent to find beta. Now, this technique can also be used to fit polynomials of more than one variable. For example, to fit a two-variable quadratic to some data, a quadratic that looks like the expression shown over here, with data that looks like this, we use as regressors the values x1 and x2, as well as x1 squared, x1, x2, and x2 squared. And we create the matrix X as usual. From there onwards, it is very straightforward to write down the normal equations and to solve for the vector of beta values. Finally, we will briefly consider nonlinear regression. In nonlinear regression, we attempt to model the data xi, yi as yi is equal to f of xi plus epsilon I, where f is a not necessarily linear function which depends on some parameters theta, a parameter vector theta equals theta 1 up to theta m, and the epsilon i's are mean zero noise terms. In multiple linear regression, the vector theta of parameters would just be the vector of betas. Fitting a polynomial can be considered as an example of nonlinear regression because a polynomial of degree greater than 1 is nonlinear. However, we managed to rephrase this nonlinear regression problem as a linear one. It is nonlinear in x, but it is linear in 1x, x squared up to x to the m minus 1, and so can be rephrased as a multiple linear regression problem. In general, however, the least squares estimate theta hat is given as that argument which minimizes the sum of the squares of the differences between the observed value yi and the predicted value f theta xi. In other words, theta hat minimizes the distance between the observed value of y and the model predicted value of y.